Så var inde i supermarkedet, så en bilafdeling, så står der bare sådan en shaker og bare kilo hakkeoksprid i ovnen fra
Skal vi køre løs? Ja. Hello. There's been a misunderstanding. So Ulrich is actually giving the lecture in the next lecture hall in Danish, but everybody is of course welcome here. So the talk today is about Gauss theorem. So I will repeat what Gauss theorem is about, and then I will take a couple of examples. So the starting point is, of course, the flux integral, or the orthogonal surface integral. But just to give the context, we have a surface, draw it like this, and we have a coordinate system x, y, z. Then again, we have a parameter space in order to describe the surface here. It's given as this rectangle, and we have the parameters u and v, and u goes between a and b, and v goes between c and d. And then we have this parameter, or this parametric representation, r of u comma v. And this is, of course, given in terms of the coordinates, or the coordinate functions. The first coordinate x is a function of u comma v, y is a function of u comma v, and z is a function of u comma v. So these three functions, and then again you have that, I could write it here, u goes from a to b, and v goes from c to d. Also, you're given a vector field. We're talking about the flux integral. So, and we give a direction to the surface. That is, we have a normal vector to the surface, and this is of importance. If you somehow or the other get this direction of the normal vector wrong, then the result is only a change of sign in the flux integral. But you should be careful when you look at that. So now I can define the flux integral. It's the flux of a vector field with respect to this surface. So this is my surface here, FR, indicating that we have this parametric representation for the surface. And it's simply defined as the dot product between the vector field and the normal vector, and then you integrate across the surface, or you sum up all contributions in this fashion. And then again we have that given the parametric representation, we can interpret this integral here as a double integral. So it'll be the integral from A to B and from C to D. And then you have the restriction of your vector field to the parametric representation in this way. And then you dot it with this normal vector here. This is a normal vector to the surface. You have the dot or the cross product of two tangent vectors, and then you get a normal to the surface. And then you have du dv. The vector field is given by these three functions, and these are each of these are functions of three variables, x, y, and z. The normal vector you use here is a unit normal vector, and this is given as this cross product, and being a unit vector, you simply divide it by the length of this vector, like this. But when you compute this double integral, you should remember the Jacobian, and the Jacobian for this parametric representation, it's given by this length of the normal vector. So r, the derivative with respect to u, cross the derivative with respect to v. So you can see when you put in this unit normal vector and you multiply by the Jacobian, you get rid of this denominator here, and you end up with this result. Now, I'm going to give you Gauss' theorem. And we have a solid field omega you have y here and x, and I simply just draw it like this. But it's a solid field and it has a boundary. You write it in this way, this special D type here, and this is the boundary of the solid field. And it's important that it is a closed boundary. That is, it is actually it's enclosing omega. And it's enclosing omega completely. Also, it is important for the theorem that I'm going to write down in a while, is that you have an outward pointing normal vector, or normal unit vector is outward pointing. So if this is the case, this is what we're looking for. It's the flux of the vector field through this boundary of my solid. If this is the case, then this is the volume integral of the divergence of the vector field, like this. And remember, the divergence of the vector field is simply the first coordinate function differentiated with respect to x plus the derivative of the second coordinate function with respect to y plus the third coordinate function with respect to z. This is simply a function from R3 into R. Now, what if the divergence of... Also, you write the divergence as this dot product, where you have the Nabla operator times v. You have seen this before. And the Nabla operator is d dx, d dy, and d dz. So, if this divergence is constant, equal to some constant, then this integral here becomes particularly simple, because then you have the divergence of, I just write it again. Now, this is a constant, and being a constant, you can put it outside the integration sign. So you end up with this formula here. And this one, this integral here is simply the volume of omega. So this is the volume. And for many simple geometries, you know the volume without making any parametric representation or so. So this is easy. You just compute it in this in this fashion. Well, in particular, if the divergence is 0, then the flux is 0. Then I could write then the flux, and then I write this, is equal to 0. And if the divergence of a vector field is 0, the vector field is called divergence free. And there are numerous examples of divergence-free vector fields. That is, if you can write your vector field as the curl of another vector field in this fashion, then you know that the divergence of this field here is equal to 0. So a vector that can be written as the curl of this in this fashion is divergence free. If you know that a vector field is divergence free, then you can show that it is possible to find a W so that this holds. And in a sense, you then have an integral of this equation here, the divergence of the vector field equal to 0. And we will look at that at the very last lecture when we are having, when I'm talking about Stokes' theorem. So in the exercises today, you should work with various forms of Gauss's theorem, and you should do that. But in order to show how you actually apply Gauss's theorem, I have a couple of examples that I want to go through. And these examples are the extra exercises on the agenda this afternoon. And let me just, this is wrong. Yeah. Let me take the first example. I think it's exercise 5 or so on the exercise set. And here you have this vector field, x, y, z, is equal to x cubed plus xy squared, and then 4y z squared minus 2x squared y, and then finally minus z cubed. So this is pretty ugly. Let's take our solid field, and it is described by this set of points here. X squared plus y squared plus z squared is less than or equal to a squared. So it's a sphere of radius a. This solid here. And we want to calculate the flux of the vector field out of the boundary of the sphere. So it's right here. It's a sphere in R3, and its center is at the origin, and the radius is equal to a. Now, I start by writing down the field, or the set of points, for the boundary. Here you have in R3, and here you simply just use the equality sign here. You get x squared plus y squared plus z squared equal to a squared. So this is the boundary. And in order to compute this flux integral, if you should do it in the ordinary way, then you need to Let me write it down. You have the flux of your vector field, and let me just, I should first introduce the parametrization of this one. And here I use a standard parametrization. You have R, U, and I use here W. No, I use V and W as parameters. And V is the angle from the North Pole to the point. Let me just show you this. Have X, Y, Z, and then you have a point on the surface, and then this angle here is V, and if you make the projection down in the XY plane, then W is this angle here in my notation now. So it'll be A, and then it will be sine of V, cosine W, then it will be A times sine of V times sine W, and then finally A times cosine V. So this is a standard parametric representation of this spherical shell. And I should say that V runs from 0 to pi, W runs from 0 to 2 pi. So when I write down this flux integral with this parametric representation, I integrate from 0 to 2 pi, and from, what did I take first there? 0 to pi. And then I take the restriction of the vector field to my parametric representation. And then I multiply by this vector here. And then VDW. But look at the vector field. It will be hard work just to write it down, and then to compute it would be even harder. So let's use Gauss in this, or start by looking at the divergence of your vector field. So you should differentiate this with respect to x. You get 3x squared plus y squared. And then you should differentiate this with respect to y. You get 4z squared, and then minus 2x squared. And then finally here you get minus 3x squared. So when you collect
The last term.
z squared, sorry. Thank you. So when you collect terms, you get 3 minus 2, that is x squared, plus y squared, plus z squared. And that looks pretty simple. It's not a constant divergence, so you cannot just take it outside your integration, but it's okay to work with. So, what I'm going to do now is that I'm going to, well, let me first take the parametrization. I'm going to use this for, in order to calculate the integral, get R of u. Now I use a third parameter because I'm going to parameterize the whole sphere, not just the surface. So use previously introduced angles v and w, but I'll also use a radial variable. So u, v, and so it looks like this. You have u sine v, cosine w, u sine v, and then sine w, and then finally you get u cosine v. And your parameters, they run from 0 to a, and v still runs from 0 to pi, and w runs from 0 to 2 pi. So I can use this parametric representation when I write down the divergence, but I also need the Jacobian in order to compute this this volume integral of the divergence. And we have looked at it before, or you can look it up, because I don't think I have time to derive this result, but the Jacobian function for this parametrization here, it's a numerical value of this determinant of this matrix, where the first column is r prime u, the second column is r prime v, and the third column is r prime w. So, and so you take this parametric representation, you perform this, take the determinant, and then take the numerical value, and you end up with the numerical value of u squared times sine v. So, and you can see, since we have chosen this parametric representation, v is between 0 and pi, and thus sine v is positive, or 0 at the endpoints. But you can just write it as u squared times sine of v. So now we are ready to calculate this volume integral, the volume of the integral of the divergence of v, and it should be this function here should be taken or restricted to this integral, or to this parametric representation. And then you should multiply by your Jacobian, and then you integrate with respect to du dv, dw, and yeah, I should write it. This is my integral. And I now interpret this as a triple integral. So you integrate u from 0 to a, v from 0 to pi and w from 0 to 2 pi. So this is how it looks. Let me just put in this parametric representation in the divergence. We calculated the divergence as x squared plus y squared plus z squared. So the divergence of v of this is, I take the first coordinate here. I get u squared sine squared v plus, or times cosine squared w was the first one, and then plus the y squared, which is u squared sine squared sine w squared. So that is u sine, or then sine squared. And then finally, I get u squared like this. And this can be reduced, because you see here you have a common factor for the first two terms. It's u squared sine squared. Put that outside a parenthesis, and then you get what is left is cosine squared w plus sine squared w, and then plus y squared cosine. Now this is equal to 1, and you are left with these two terms, and you can put u squared outside, and you get sine squared plus cosine squared v. And again, this is equal to 1, so the result is u squared. Well, if you look at this, then this is the square of the distance to the origin, x squared plus y squared plus z squared. So actually you should get the result that this sum here should be equal to u squared. Okay, let's put this in. We get the integral from 0 to 2 pi, the integral from 0 to pi, and the integral from 0 to a. And then I put in u squared, and then I put in my Jacobi function, which is u squared times sine of v, and then you get du dv. And you can see that if you integrate, this is u to the fourth power, and an indefinite integral of that is u fifth divided by 5. So you get u, and you should take this between 0 and a. And then what is left, there's no w here, or sorry, now there is, but there's no, the integrand doesn't depend on w, so it's simply just the interval length. And then you have the integral of sine of v, and this is minus cosine v from 0 to pi. The lower part doesn't give you anything, so you get a fifth times 2 pi, And then when you put in the upper limit, you get -1 and -1, that is 1, and then -1, so you get a 2. So the result is 4/5 pi and a. So this is a lot easier than actually doing the flux integral, even though you're using Maple. Okay. I have still an example, and this is example. I think it's exercise 6 of today's lecture. And here you're given this solid here. I should say that it's in all of our 3. X divided by a squared plus y divided by b squared plus z divided by c squared. And this is less than or equal to 1. Can anybody tell me what that is? What kind of solid is that? Yeah. Ellipsoid. Yeah. 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 So with the axis A, B, and semi-axis A, B, and C, let me see if I can draw such a thing here. Let's say A is this one, and B is this one, C is like this. Then you have, say, and then you will have something like this. It's not that good. Okay. But it will be something like an American football or what have you. But it's an ellipsoid, and I also have a very simple vector field. 3x, 3y, and then minus z. So the parametric representation of an ellipsoid is a bit cumbersome. So if you want to put this into your equation and you want to do this integration, then it will be somewhat difficult. So when you look at something like this, try and look at this this vector field here, because that looks simple. Let's try to calculate the divergence of your vector field. So I should differentiate with respect to x, 3 plus, and then plus 3, and then minus 1. So actually my example, I think it's also like that in the exercise. There's 2 here, so it should be 2. But the important thing is that it's equal to the constant 4. And since this is the case, then it's very easy to compute the flux. So you get this volume integral of the divergence of V. And since this is constant equal to 4, you can put it outside this and you get the volume of, and this you can look up, this volume, if you don't know it. There is one simple case where you perhaps knows where you know the formula for the volume, and that is if A and B and C are equal, because then it's a sphere. No, the volume of a sphere is 4/3, and then R, you have R cubed. This is the volume of a sphere. But now these different radii are not equal. So this is just a way to remember it. So it will be A, B times C. So it'll be 16 Sorry? Yeah. It's also there for the sphere, of course. Yeah. So I only have one last thing to tell you today, and this is something that you might find useful later today. I did it the last time, and this is another way of defining the flux. Let me see if I can find what I said. And I'll just give you the definition for this. And this was about volume expansion. And here you imagined that you have a surface. You have a surface, F, and it floats along the flow curves of a vector field. So you have the vector field, and then you calculate the flow curves, and then you follow your surface along this. And when you do so, then this surface here will sweep a solid. I think the example I did is that I took this rectangle here, and then I took a unidirectional vector field, and here this rectangle will flow with the vector field, and at a certain time, later time, this has swept a volume here. So this is time 0, and this is time, like this. I write here, when the surface F floats along, I write here a spatial field is swept. And in this case here, it's this box here that is the spatial field. If this is the case, then the volume of this spatial field. I should state here that I use omega t to denote this spatial field. It is a function of time. Then the derivative, or the rate of change, of this volume taken initially, that is when t is equal to 0, just when it started, and then you calculate the rate of change. Then this is the flux of your domain, or of your vector field with respect to this surface F. So this is what I planned for today. So good luck with the exercises. Yep.